Okay, we're going to talk about relations today. Suppose you have a set A. Let's say this set has, we're just going to put some numbers in here. It's not important particularly what they are. Okay, and another set B. Okay, let's do that. Let me make that 6 look better. Okay, now, what if I say that I'm going to write down how the numbers in A, which they might not even be numbers, they might be letters, so let me say elements, how the elements of A are related in a certain way to the elements of B. And let me draw this with an arrow diagram. Actually, I can do, I think, let's see, I can do a nice perfect shape like this. Okay, so let's put the numbers from A here. It doesn't matter where I locate them. Okay, and then let's do something similar for B. Whoops. Ah, here we go. Okay. All right, now, what if I draw arrows like this? One arrow going from 2 to 4. So 2 is related to 4 in some way. I'm not telling you yet what I have in my mind. And maybe 2 is also related to 6. And maybe 2 is also related to 8. So 2 is related to all 3 of the numbers. Okay. And then let's do 4 is also related to all 3 numbers. But 5 is only related to 6 and 8. And 7 is only related to 8. So there's a diagram showing how I want the numbers in A to be related to the numbers in B. I'm not saying what the relation is here. I'm just telling you which numbers are related to others. Okay, now this relation goes one direction. So I was about to say I'm telling you which numbers are related to each other. Okay, kind of like cousins, you know, and things like that. Okay, I stopped myself because that's not what I want to say, because that sort of a relationship goes both directions. This one only goes one direction. Okay? Now, I can do this. Let's call the relation R. Okay? Let's just call it R. And I like to draw an arrow like this. Okay, so that's saying this. R is a relation from A 2b. Okay, and this set A is called the domain of the relation, and the set B is called the codomain, not the range. In fact, I'm going to add another number to B. Let's add a 1 in there as well. Okay, so you see why B is not called the range, because there are no elements of A that are related to the number 1 in B. That's why B is not called the range. Okay, it's called the codomain. Okay, now I can write this. I can write 2 is related to 4. We write like that. 2 is also related to 6. And 2 is related to 8. I can say that 4 is related to 4. 4 is related to 6. And 4 is related to 8. I can say that 5 is related to 6. 5 is also related to 8. And I can say 7 is related to 8. Okay, so here's one way of depicting a relation, is with this kind of a diagram. Certainly very visual. Really gets the point across. But a couple drawbacks. Takes up a lot of space, tends to be time consuming to draw. And one of the biggest drawbacks here is the strength of that diagram is that it's very visual and you can see the relationships, but that strength can also be a weakness in this particular case. If there's too many arrows, then it just gets really hard for your eyes to follow the arrows. And I would say that this is almost bordering on that sort of a situation. It's not too crowded, but there are certain places in this diagram where the arrows overlap each other so much that it gets a little bit hard to follow them. Okay, so arrow diagrams, very nice, very visual. Tend to take a lot of room and time, though, to draw, and can get way too crowded, in which case they just become almost useless. Okay, so here's another way of representing a relation where you don't have to worry about overcrowding. This is usually very quick to write down this. You lose the visual aspect, which is kind of a bummer, but it's quick and it's easy. Okay, but it makes you ask the question, I wonder if there's an even more condensed way to write this. And there is. And here's another drawback too, is that writing the relation the way I did there in yellow, notice it doesn't use any of the symbols that we've learned in this class from set theory. And you might say, well, yeah, but we've just learned a new symbol, which is that capital R, and that's true. But I do have the question, could I represent the same relationships using symbols that we already knew? And you see, I can take this 2 is related to R. One second here. And I can rewrite that by just writing the ordered pair. Oh, did I say 2 is related to R? I meant 2 is related to 4. I can represent that by just writing the ordered pair 2, 4. And just asking you, when you see that, when you see the ordered pair 2, 4, say to yourself, 2 is related to 4. Okay? Two is related to 6 can just be written as the ordered pair 2, 6. And so on and so on. I'm going to go ahead and fill in the rest. Okay, there we go. So each of the relationships can be represented by an ordered pair. And the relation R is the collection of all of those relationships, which means the relation R is the collection of all of these ordered pairs. What's another name for a collection? It's a set, right? A set is just a collection of things, right? So therefore, I can write that R, let me make this a little thicker here. I can write that R is the collection of these ordered pairs Okay, there we go. So, you see what I'm saying? Let me just review, okay? This type of a thing here, that's called a relation. A relation can also be represented like this. Each individual relationship can be represented as an ordered pair or like this. Okay? So in yellow, I've shown you how to write individual relationships. In blue, I've showed you how to write the entire relation. Okay, got that? Now, I want you to notice something really important. If I write the relation this way, what is that? That's just a set of ordered pairs, right? Do you notice that this is just something important? This is a subset of the Cartesian product of A with B. So this is really important for you to understand. Every relation from a set A to a set B can be represented by a subset of A cross B. And let me say the same thing in the other direction. Every subset of A cross B represents a relation from A to B. I'm going to put that here in writing. Every relation from A to B can be represented as a subset of A cross B. Also, every subset of A cross B represents a relation from A to B. Whoops. So we could actually say that relations are subsets of Cartesian products, and that would be a mathematically correct thing to say. Okay? Now, here's something just kind of for fun. That relation that I've showed you right here is actually a relation that you already know. Some relations represent things that you know already, and some don't, okay? Look at that and see if you can tell. What I'm trying to say is this. When I drew those arrows in that diagram up there, I was following a certain rule in my head. That's what I'm trying to say. Okay, I was following a certain rule in my head to determine where I should draw the arrows. If you were to look at that, pretend this is like a game, a riddle. Look at that diagram. See if you can figure out what rule I was using. Can you figure it out? Okay, I'm going to give away the answer. Pause it if you want to wait, if you don't want a spoiler, okay? The rule I was following is the rule is less than or equal to. Okay, do you see that? 2 is less than or equal to 4. 2 is less than or equal to 6. 2 is less than or equal to 8. 2 is not less than or equal to 1. 4 is less than or equal to 4. 4 is less than or equal to 6, and 4 is less than or equal to 8, but 4 is not less than or equal to 1. 5 is less than or equal to 6, and 5 is less than or equal to 8, but it is not less than or equal to 1, and it's not less than or equal to 4. And 7 is less than or equal to 8, but 7 is not less than or equal to 1, it's not less than or equal to 4, and it's not less than or equal to 6. So that relation that I drew is in fact the relation less than or equal to. Okay, and in fact, in this column here, since there's a symbol for less than or equal to, I could have used that symbol. Okay, so that's what a relation is. Now, you can have a relation that goes from a set to itself. Okay, a relation from, let's say, from a set A to A. I'm going to do a different one this time here. Let's say A is the set. This time let's say 1, 2, 3, and 4. Okay, and I'm going to draw a relation from A to A. All right. So 1, 2, 3, 4, 1, 2, 3, 4. Let's put the arrows in there. Okay, and I'm going to do the relation like this. Let me think for a second here. Okay, I don't want to make it too crazy. Let's do this. 1 is related to 3. And it's also related to itself. I would like to do that. Two is related to itself and also 4. 3, I want to make related to 1 and itself. And 4, I would like to make related to 2 and itself. Okay, so there's a few things I can write. I can write 1 is related to 1. Let me make this smaller. I can write 1 is related to 1, and 1 is related to 3, and 2 is related to 2, and 2 is related to 4, and 3 is related to 1, and 3 is related to 3, and 4 is related to 2, and 4 is related to 4. Or I can write the relation equals the set of ordered pairs 1, 1, 1, 3, 2, 2, 2, 4, 3, 1, 3, 3, whoops, 4, 2, 4, 4. Now, relations do not have to follow some specified rule. I could literally just put in random arrows. Okay, however, I didn't. I actually did follow a rule this time, just like last time. Can you figure out the rule? See if you can figure it out. It's not as simple as the last one, though. Okay, the rule is this. A number is related, let me say this way. A number in the domain is related to a number in the codomain if and only if the number in the codomain has the same parity. Okay, so I can write a couple of things. I can say x is related to y if and only if x and y have the same parity. Okay, that's the relation that I drew in that diagram. Or another way of writing that is to say x comma y is an element of the relation if and only if x and y have the same parity. Okay, Now, notice that the domain and the codomain are the same in this particular case. So I would say, first of all, this would be correct to say R is a relation from A to A. That is mathematically correct. There's a correct use of language. But there's something else I could say that's slightly shorter, is I can say R is a relation on A. Okay, so on A is the same thing as saying from A to A. Just using the mindset that if the domain and codomain are the same, then why say that name twice? Okay? Now, you might also ask this question. Since the domain and the codomain are the same, then why draw them twice in the diagram? And that's a good point, and you don't have to draw them twice. You could have done this, or I could say I could have done this. I could have just drawn A once. Whoops. I'll make it a little bit bigger here. So, okay, so it's not crowded. I could have done this. And I could have said 1 is related to itself, and it's also related to 3. Two is related to itself, and it's also related to 4. 3 is related to itself, and it's also related to 1. 4 is related to itself, and it's also related to 2. I could have drawn the diagram that way. Okay, it's just a matter of how you'd like to draw it. Okay, so those are relations. Now, let's get a little bit more specific. Suppose R is a relation on A. Okay, there are some adjectives that R might earn or it might not. There's 3 in particular. Okay, so R is called reflexive if X is related to itself for every X in A. Actually, I'm gonna word it like this. If for every X in A, we have X is related to itself. Another way of saying that is to say R is called reflexive if the ordered pair x comma x is an element of R for every X in A. So that's reflexivity. Okay? All right, here's another adjective that a relation might have. R is called symmetric if x being related to y implies that y is also related to x. Remember, when we say a mathematical relation, it does not necessarily work in both directions. Remember this one up here. Let's look at the first example. Sorry, that's not the first example. Here's the first example. So notice that 2 is related to 4, but 4 is not related to 2. Okay, so this is a relation that is, you could say it's unidirectional instead of bidirectional. Okay, but what's better is to use the correct terminology and say it is not symmetric. Okay? If x being related to y automatically means that y is also related to x, in that case you would call it a symmetric relation. Okay? Or another way to write that is to say R is called symmetric if we let's write it like this. If for every xy that is in R, we have yx is also in R. So again, I'm going to go back to that first relation and show you that it's not symmetric, because I'm going to use the same example, because 2, 4 is in the relation, but if you look there, you see that 4, 2 is not. Actually, to be honest with you, there's even so that's why this is not symmetric. Okay, yes. But I also just realized something, and this does not ruin the examples that I've said so far, but I just happened to notice this, that this could not have possibly been symmetric anyways, because the domain and the codomain aren't the same set. This is not a relation on a set, so it could not possibly have been symmetric. Okay, let's look at the second example here. Is this one reflexive? Let's look here. The easiest way to tell is probably here. Let's look at that. Okay, and I want you to notice a few things here. Notice that 1, 1 is in the relation, 2, 2 is in the relation, 3, 3 is in the relation, and 4, 4 is in the relation. What's that tell you? It tells you the relation is reflexive. Every number in A is related to itself in the relation R. Okay, let's see if this one is symmetric. This takes longer. So let me ask you, let's do this. So here's 1, 1. Let me ask you this question. I'm going to flip that order. And instead of 1, 1, it's going to become 1, 1. Okay, is 1, 1 in there? Yes, it is. Now, that one wasn't interesting because the first number and the second number are the same, but it becomes more interesting here. Here's 1, 3. I'm going to flip that order and get 3, 1. Can you find 3, 1 in the relation? Yes, right there. Okay. Here's 2, 2. Is 2, 2 also there? Yes, it is. Here's 2, 4. Is 4, 2 also there? Yes, it is. Here's 3, 1. Is 1, 3 also there? Yes, it is. Here's 3, 3. Is 3, 3 also there? Yes, it is. Here's 4, 2. Is 2, 4 also there? Yes, it is. And here's 4, 4. Is 4, 4 also there? Yes, it is. So that relation is symmetric. So it is reflexive and it is symmetric. Okay, another way to do that is to look here for reflexivity. You look to see if every number is related to itself, and it is, so that means it's reflexive. For symmetry, you have to see if every arrow can be reversed. And they can. Every arrow can be reversed. So it is symmetric. Okay? So having the same parity is reflexive and symmetric, at least on this particular set. But even if that set was all real numbers, it would still be reflexive and symmetric. Okay, now one more adjective called transitivity. Okay, R is called transitive if X being related to Y and Y being related to Z together imply that X must be related to Z. Another way of saying that, R is called transitive if XY being an element of R and YZ being an element of R imply that XZ is an element of R. Let's look at our second example that we saw that it is reflexive and symmetric. Is it transitive? This one takes a long time to check because there's if you check it manually, there's so many things to check. Let me think for a second of how many it would. There's 8 elements of our relation. To see if this is reflexive, I would have to check 64 possibilities. I'm not going to check all 64 with you, but I'll point out some of them. Whoops. Here are the types of things you would have to check for transitivity. You would have to say, for instance, 1, 3 is in there, and 3, 3 is also in there. So 1 is related to 3, and 3 is related to 1. Does that imply that 1 is related to 1? And the answer is yes, because 1, 1 is there as well. Okay? Those are the type of things you'd have to check. Here's another one, just as an example. I could say 2 is related to 2, and 2 is related to 4. Is 2, meaning this here, related to 4, meaning this here, and the answer is yes, because that's right here. Okay, you see how that works? If you're looking at the diagram with arrows, then this is how it looks. You would ask yourself, if I follow one arrow, let's say from here to here, let me choose a different example. If I follow one arrow, let's say from 1 to 3, and then from there I can follow another arrow from 3 to 1, could I have gotten from the beginning to the end with only one arrow instead of needing 2? And the answer here is, in this case, yes, I could have just gone on this arrow here. You see, so that's an example of transitivity, but the relation is only transitive if all such possibilities exist. So transitivity takes a long time to check. Okay? Now, here's another word. R is called an equivalence relation. If it is reflexive, symmetric, and transitive. Okay, let's look back at our example. Is this relation, the relation of having the same parity, is that an equivalence relation? Then the answer is yes, because we checked it and we saw it's reflexive, it is symmetric, and even though we didn't check transitivity thoroughly, I think by looking at it for a few minutes, you will see that it is in fact transitive. So having the same parity is what's called an equivalence relation. Okay, and what that means, the reason why we call it an equivalence relation is this. You're probably used to equivalent meaning equal to, and so you might think, well, that's weird to call this an equivalence relation because we said that 2 is related to 4, but certainly they're not equal. But there is a reason why we call it an equivalence relation, and that is this. If the only thing that you care about is parity and nothing else, so oddness and evenness, if that's the only thing you care about and nothing else, then as far as you care, 2 and 4 are the same number. Okay, you gotta don't ignore the first half of that sentence though, because that's the important part. If the only thing you care about is parity. Okay, let's talk about this for a minute. I'm not going to write anything now, so you have to listen very carefully. Okay, I'm going to play devil's advocate on that. So I'm going to say it again. Having the same parity is reflexive, symmetric, and transitive, so it's an equivalence relation. That means if the only thing you care about is parity, then 2 and 4, as far as you care, are the same number. Now, you might say, well, that can't possibly be true because, for instance, 2 times 3 is 6, and 4 times 3 is 12. So if 2 and 4 are the same number, as far as I'm concerned, then that means 6 and 12 would have to be the same number. And my answer to that question is, yeah, you're right. If the only thing you care about is parity, then 6 and 12 would be the same number. Because why? Because they have the same parity. See what I'm saying? All right, now, one more concept to cover. If you have an equivalence relation, oh, by the way, sorry, let's look at a new example for a minute. Same set, okay, the set of numbers 1, 2, 3, and 4, same set, but this time I'm going to do a different relation. Okay, 1, 2, 3, 4. I'm going to do the relation is less than. So it's true that 1 is less than 2, 1 is less than 3, and 1 is less than 4. 2 is less than 3, and 2 is less than 4, and 3 is less than 4, and that's it, right? This represents the relation is less than. Okay, that represents the relation is less than. Is that an equivalence relation? No, it is not. It in fact fails reflexivity and symmetry. It's not reflexive because 1 is not less than 1. 2 is not less than 2. 3 is not less than 3. 4 is not less than 4. Okay? It's also not symmetric. 1 is less than 2, but 2 is not less than 1, and so on and so on. It is, however, transitive. If one number is less than a second number, and that second number is less than a third number, then the first number is going to be less than the third number. So it is transitive, but it's not reflexive or symmetric, and therefore it's not an equivalence relation. Okay? That is the relation less than. I could make it reflexive by changing it to less than or equal to, and then that would add these 4 relationships, which means I would get 4 more ordered pairs. So now it's reflexive because every element of A, remember A started out with A, it's the set 1, 2, 3, and 4. And we see that every element of A is related to itself by the relation less than or equal to. So it is reflexive. The relation less than or equal to is reflexive on A. It is also transitive, but it's still not symmetric. For instance, 1's related to 2, but notice that 2 is not related to 1. What else could I say? 3 is related to 4, but 4 is not related to 3. Okay, so it's still not symmetric. It's reflexive and transitive, but not symmetric. So this is not an equivalence relation. Okay, once again, why do we use the word equivalence? If all I care about is less than or equal to, so let's say order, if all I care about is order, okay, then I can say that the numbers 1 and 3 are not the same in my mind, because 1 comes before 3, but 3 doesn't come before 1. So if I care about order, then in my mind 1 and 3 have to be kept separate. They are distinct concepts. Whereas going back up here, if what I care about is parity, being even or odd, then as far as I care, 1 and 3 are the same. They represent the exact same thing. Okay? They represent the same concept, which in this case would be oddness. Okay? Now, there's something that I wanted to say before, and I said let's wait a minute and look at something that's not an equivalence relation. So we did that. Now I want to get back to equivalence relations. Okay? If R is an equivalence relation, on A, then R partitions A into disjoint. If you don't know what that means, hold on a second. Subsets. Disjoint means having no intersection. Okay? Let's look back at our equivalence relation example here. Sorry, I know the screen is shifting a bunch. That's because my computer is starting to, for some reason, get bogged down, and I don't know why. Okay, so this is an equivalence relation, having the same parity. A is, let me make this smaller so we can see. Okay, A is the set 1, 2, 3, 4. Okay, look up there in the top corner where it says 1, 2, 3, 4. I'm going to underline in green all of the numbers that are related to 1. It's just the two of them, 1 and 3, right? I'm going to underline in red all of the numbers that are related to 2. So do you see what I've just done is I've just partitioned A into two subsets, a green subset and a red subset. The green subset consists of 1 and 3. The red subset consists of 2 and 4. When I say the word partition, what that means, the word partition means that these two sets have nothing in common. Their intersection is empty, but they make up the entire set A. Their union is A. That's what the word partition means in set theory. Okay? Now, those sets, the green one and the red one, those are called equivalence classes. So let's go back to where we're writing the definition. If R is an equivalence relation on A, then R partitions A into disjoint subsets. Let's change that period to a comma, and let's say called equivalence classes. Okay, so going back up here, that green set right here, of course I wouldn't say that's the green equivalence class because maybe somebody else doesn't have colored pencils and they didn't use green. You would say that is the equivalence class of 1, or you could call it the equivalence class of 3. The equivalence class of 1 and the equivalence class of 3 are the same equivalence class. They are the set consisting of 1 and 3. The other one you could say that's the equivalence class of 2, or it's the equivalence class of 4. Okay? And by the way, an equivalence relation oftentimes gets this symbol, an equal symbol except with 3 bars instead of 2. That is often used for equivalence relation. Anytime you see that, it means you have an equivalence relation. So up here, I can say, and it would be correct to say, 1 is equivalent to 3. 4 is equivalent to 2. 3 is equivalent to 1. It's unnecessary to say 3 is equivalent to 1 because I know equivalence relations are symmetric. So when I said 1 is equivalent to 3, I was automatically saying also 3 is equivalent to 1. So it's not necessary to say that separately. Okay, and I said 4 is equivalent to 2, but I could have just as easily said that 2 is equivalent to 4. Okay, now the only drawback to this symbol right here, that's just a generic symbol for equivalence relation. It doesn't actually portray to you what the relation is. If I wrote that, you have no way of knowing that that relation is having the same parity. For all you knew, that relation might have been, well, I don't want to just make up something off the cuff. Okay, but you see what I'm saying? Equivalence relations, we have this generic symbol. If a relation is an equivalence relation, then you can use that symbol. It's just a generic symbol that stands for is equivalent to. So you could use that symbol for any equivalence relation. But if you're talking about a specific equivalence relation, like having the same parity, and you're going to use that symbol, you have to describe for the reader that that symbol is going to be standing for having the same parity. And then if you want to talk about a separate equivalence relation later, you'd have to tell the reader, okay, now we're talking about a different equivalence relation. Okay? Let's see where we are on time. Oh, that's a long, okay, we better stop. All right, we'll do more in the next lecture.